In this video, I will talk about inverse functions, one-to-one functions, which are functions that have an inverse, then the horizontal line test, which allows us to identify one-to-one functions, and then I give you two examples of how to compute inverse functions. Given a function f, then the inverse is denoted by f to the minus 1, and this is another function which kind of undoes f. So it kind of does the opposite of f. F of minus 1y is equal to x, if and only if f of x is equal to y. So for example, if f of 2 is 11, then the inverse of 11 is 2, right? So the function undoes what the original function has done. In general, if f of a is equal to b, then f inverse of b is equal to a. More specifically, for example, x to the power of 3, so we have f of x is x cubed, then the inverse function is the third root of x. There's one particular function which is its own inverse. This is kind of a little miracle. So the function 1 over x has the inverse 1 over x. This is cool. Or if we have the third root of x as a function f, then the inverse is x cubed, so it goes both ways. How do we find inverse functions? Well, not all functions do have an inverse, and one of the most popular examples of not having an inverse is the parabola, f of x is equal to x squared. In fact, if I sub in 2, then I get 4. If I sub in minus 2, I also get 4. So there are two values of x, 2 and minus 2, where the function f has a value 4, and this is also indicated here in the graph. Right? We have 2 points, this one and this one, where the function is equal to 4. So what is the inverse, f inverse of 4? Is it 2 or is it minus 2? Well, in this case, we would say the inverse does not exist. A one-to-one function never takes the same value twice, meaning that f of x1 is not equal to f of x2 whenever x1 is not equal to x2. So the parabola up here is not one-to-one. We can identify those with a horizontal line test. So we draw a horizontal line which crosses a function, and if it never crosses a function twice, or more often than twice, if it only crosses a function once, then the function satisfies the horizontal line test, and it is a one-to-one function. So here the parabola, for example, the horizontal line at 4 touches twice, so this does not satisfy the horizontal line test. One-to-one functions have inverses, so these are the functions which have inverses, and then the range and the domain flip. So the range of f becomes the domain of f inverse, and the domain of f becomes the range of f inverse. So how do we compute inverse functions? And I would like to entertain two methods. One is the classical method, which you probably learned in this form or a similar form in high school. But then I like to advance this method a little bit further to use it for scientific examples. And there's one small modification which I like to explain. But first let's look at the classical method. So what do? We write y is equal to f of x, we solve for x, and then we switch x and y. So let's do that in one example. F of x is the square root of x minus 2 plus 3. Okay, so then I write y is equal to square root of x minus 2 plus 3. And now the second step is to solve for x. So I move the 3 to the other side, I get y minus 3 equals square root of x minus 2. And now I take the square, so I do y minus 3 squared is equal to x minus 2. And then I can solve this for x. I move x to the other side, so we get x is equal to y minus 3 squared plus 2. Now I solved this for x. And then the last step says switching x and y, meaning I get the function y is equal to x minus 3 squared plus 2. All right. And so then this is my inverse function, f inverse of x. So far, so easy. Now how is this with the domain and range? So what was the domain of the original function? In the original function, I can only sub values of x which are larger or equal to 2. Otherwise, the square root would be negative, right? So then the domain, I write it as an interval, would be the interval 2 to infinity. And then the range of f, these are all values which come out. And so if I sub in 2, the lower boundary, then the value of f is equal to 3. Right? You see that. If I sub in 2, I get 3. If I sub in larger values of x, I get larger values of f of x. In fact, I go to infinity if I use arbitrarily large numbers. So the range here is 3 to infinity. Okay, and then this flips for the inverse. So the inverse now has a domain of 3 to infinity and a range of 2 to infinity. So you don't even need to think about this. It just follows automatically by switching. Okay, so the range becomes the domain and the domain becomes the range. Let's look at these functions. Here they are. So the blue function is the original function f of x, square root of x minus 2 plus 3. And you can exercise something we have learned earlier, which are shifts of functions. Right? So the blue function is like a square root function, but it has been moved up by 3. It has been moved up by 3. And then it has been shifted to the right by 2. And these are values you can identify here in your original function. This is not the content of this video, so I will remove this here and here and here. The red function is the inverse function, x minus 3 squared plus 2. And you see they are quite symmetrically arranged around the diagonal line. The diagonal line is the dashed line here, and there are mirror images imaged on the dashed line. Let's talk about what I call the scientific method. It's a little bit simpler than the classical method, believe it or not. The thing is, sometimes in scientific context, the variables x and y do have a meaning. For example, it could be a drug concentration as a function of time. And then we can not just simply switch x and y. So here's what we do then. We write y is equal to f of x. We solve for x as before, but then we stop. We do not switch x and y. And why we do not switch, I explain you now in an example, where we use the same function, y is equal to square root of x minus 2 plus 3, but now we give it a meaning. So let y denote the length of a fish, and x be the age of the fish. And then the formula y equals square root of x minus 2 plus 3 describes the length of the fish as a function of its age. And now the question is, find the inverse. So let's do the same thing. We write y equals square root of x minus 2 plus 3. And then solve for x, which is the same as I did before. Let's just quickly do that. But now, in the last step, I do not switch. I just stop here and I write x is f inverse of y. Actually, there's no need to switch x and y. I'm perfectly fine of defining a function which depends on y, and that gives you the value of x. Okay, so let's look how this looks like. Now, however, since the variables have a meaning, I cannot plot them in the same graph. So these are the same kind of curves you have seen earlier, but now I show them in separate graphs. And the reason is, so the blue curve is the length of the fish as a function of age. So it basically means if I observe a fish for, let's say, 6 years, okay, then I can kind of estimate that it must have a length more than 4 centimeters, say, maybe about 5 centimeters. The inverse function now gets a very different meaning. Now I have the length on the x-axis and the age on the y-axis. So meaning, let's say I catch a fish of length 4 centimeters, then I can estimate it must be maybe about 3 years or maybe 2.5 years old. In a scientific context, when the variables get meanings like length and age, then it's no longer possible to switch x for y and y for x. We need to just keep them their names, and the functions get different meanings. The original function gave me the length as a function of age. The inverse gave me the age as a function of the length. So let me summarize. So we discussed inverse functions. We saw they belong together and they form a unit. One-to-one functions are those which satisfy the horizontal line test, and they do have inverses. And then for the finding the inverse function, there are two methods. The classical methods, you would isolate x and then switch x for y. In the scientific context, however, you would just isolate x and be done, and not switch x for y.